with you, even if it is at a distance, but it is nice that we can join all together in this way. So you will wonder why the title, why do we want a quantum deformation of the Minkowski space? And this is something that has to do with gravity. You know that we are not able to resolve distances that are of the order of Planck length, because if we send a photon so energetic that will resolve that distance, then so much energy concentrated in such a small space, it will become a black hole. You can compute the size of the of the length. You can compute the length at which this thing will happen, and it is the order of the Planck length. So we say that the theory fails at that distances, and it may happen that some regularization of it comes from a non-commutative geometry. Many people have been working on that. We expect that somehow at these distances, the space-time is not more a smooth manifold, but the points become blurred or fuzzy because of certain incertitude principle that comes from the coordinates not being commutative. So there has been a lot of work on this. There are many deformations of possible of the super Minkowski space. The one that I present you here is original, is not has not been done before us, and it is the result of a joint effort with Rita Fioresi, Emanuele Latini, and Junai Razak. Along several years and several papers. I will try to present here a summary of what has been done. It will be perhaps a bit too compacted, but I'll try to be as clear as possible. So this will be the plan of my talk. We'll start saying what we call the classical conformal space and why it is interesting to look at it and its relation with the Minkowski space. We will see that it is in fact a Grassmannian manifold, and it has an embedding that is called the Plucker embedding, and probably you know very well. Then we'll see the quantum picture, and then I want you to see also the super picture, because since at those distances we don't know, supersymmetry has been proposed also for other reasons, for string theory to be consistent, and for the finiteness of gravity and other things. Supersymmetry is interesting, even when it has not been found in the LHC. Still, we think that has something to do with, it could have something to do with the real world. There is something similar to the Plucker embedding, but it's a super Plucker. You will see that it's more complicated. It's not just a straightforward generalization. I would like to talk about the quantum part, the super quantum part. This means to put the two things together, the quantum and the super, but this I will not have time, so I would say only a couple of words. So let's start with the Minkowski space. It's R1,3, which means that we have a symmetric bilinear form represented by a matrix that is has +1 and -1 in the diagonals, the way I wrote there. And as you know, the Lorentz group is the group of transformations leaving invariant that bilinear form. So it satisfies the matrices lambda that appear in this equation are matrices of the group O1,3. This is the associated quadric to the bilinear form, and we can see that the points in which this bilinear form of this quadric is equal to 0, the 0 points form a cone that is called the light cone. It is represented here I'm representing only the vertical direction, that is the time, and the horizontal direction, that is one of the coordinates. And you see that if I add the other coordinates, it will become a cone formed by the future cone and the past cone. These are events that can be reached from the origin. And then outside the light cone, there are events that cannot be reached, that are not connected casually. Well, we would like to see if a more general symmetry than just the Lorentz symmetry by requiring that this causality is preserved. So we want that this light cone to be preserved. It means that you can convince yourself that this means that the quadric we could apply transformations to the coordinates in such a way that the quadric becomes multiplied by a function of the coordinates. Here I call the coordinates x, but it's the same than the y's. This is an example of a transformation that we call these transformations conformal transformations. And it is just a dilation. By doing this change of variable, I get the quadratic form multiplied by the positive real number lambda. And these are all the possible conformal transformations. We have, we have translations. We have translations. We have dilations that are written in different way, but it's the same that I wrote here. We have, of course, Lorentz transformation, but more interestingly, we have these special conformal transformations. It can be shown that the group of all these transformations forms the group O2,4. So it's like the Lorentz group, but for a metric with signature 2,4. Indeed, we will be working with the spin group. That is, the spin group is the double covering of the connected component to the identity of SO2,4. And this is because in supersymmetry, we introduce spinors. And the spinors are representations of the double covering, but are not representations of the SO2,4 itself. So one thing that you can observe in these special conformal transformations is that they have a denominator here. B is an arbitrary vector, just like A is an arbitrary vector. B is also an arbitrary vector. And it may happen that for some points, this denominator is equal to 0. So it seems that on the Minkowski space, these transformations are not well defined. Yeah, I forgot to say that one theory that is conformal invariant under conformal transformations is the electromagnetism in empty space. Has this invariance. Even when the conformal symmetry is broken, like it's broken in many theories, it can be interesting to see how this symmetry is broken and what terms in the Lagrangian generate the breaking of the symmetry. So coming back to the points where the transformations are singular, one must add points at infinity to have a smooth action of the conformal group. We'll see later exactly which points are we going to add. So the conformal space for us, what we call conformal space, is a compactification of the Minkowski space such that it is an homogeneous space under the action of the conformal group. This is what we require. We will work with the complexification of all these, complexification of Minkowski space, complexification of the conformal group. And this is because the geometric structure that I'm going to present you is only true in the complex. So we can work in the complex all the time and at the end put a reality condition and get the results. But in the real, you don't see this beautiful structure that I'm going to present you. So these will be our groups, will be SOC 6, C and SL4, C, that is the double cover. And SL4, I will represent it in this way as a 4x4 matrix, obviously with determinant equal to 1, but I will represent it by this block 2x2 block matrices, because it will be convenient for us to make this decomposition. So one thing that we know is that SL4 acts on the Grassmannian. It has a natural action of the Grassmannian of two planes inside C4. And this will be our candidate for the conformal space. And we will see why it is so. A plane inside G24, it is given by two linearly independent vectors. And then we can for example, assume that this first minor, the minor of A1, B1, A2, B2, this minor is different from 0. So by making linear combinations of these vectors, we can get it to this standard form, where alpha, beta, gamma, delta are arbitrary, non-restricted complex numbers. So the set of these elements that can be put in this form is what we call the big cell of the Grassmannian. Here C4 is not exactly the Minkowski space, is the defining representation of SL4, and it is in some other ambience is called the twistor space, but we will not enter in the theory of twistors here. For us, we will have SL4 like the double covering of the group SOC, and we can wonder what is the group that lives invariant the big cell. Because the big cell is going to be our candidate, conveniently transformed, will be a candidate for the Minkowski space. So it happens that the subgroup of SL4 that leaves the big cell invariant is a lower parabolic subgroup. And see what is the structure, the matrix A that is completely unrestricted and it's isomorphic to C4, changes in this way. R and L are transformations of GL2, in fact, of GL2, because L and R have to be have determinant different from 0. But since the determinant of the whole matrix is equal to 1, what we have is two independent SL2Cs plus another transformation that is C without the 0. That corresponds to dilations. And N corresponds to translation. So what we have here is the double covering of the complexified Lorentz group times dilations, everything a semi-direct product with translation. So this looks like very much like the double cover of the Poincaré group. We can recover the standard coordinates by making this change of variables with here, where here we have used the polymatrices plus the identity, and see that if we compute the determinant of this matrix, we will obtain the metric on Minkowski, on the standard metric on Minkowski space. So G24, as we say, there is an action of SL4 on G24. This action is transitive. So if we take a point in G24, like for example, this pi 0 that I represented here, and we compute the stabilizer of the isotropy group of pi 0, this is the upper parabolic subgroup that is isomorphic to the lower parabolic that was the Poincaré group. But the point here that is interesting is that G24 is the quotient of SL4 by a parabolic subgroup. This means exactly that G24 is a projective variety. This is a theorem that if you have a semi-simple group here and you have it quotiented by a parabolic subgroup of it, then it is it can be embedded into a projective space. So the Fluker embedding is one possible projective space where to embed G24, and it goes in this way. We take as a vector space the order 2 antisymmetric tensors on C4, and this is isomorphic to C6. And then we know that for any plane represented by two independent vectors, one of these minors have to be different from 0. This is the condition for the vectors to span a plane. So we can make a map phi that takes this plane and gives the wedge product between these two vectors. Of course, these two vectors can change, can be different, and since all these coordinates that are the coordinates on C6 in the basis that I give you here, EI, wedge, EJ, all these coordinates cannot be 0 simultaneously, then we are in the projective space. We can go take equivalence classes and go to the projective space. So this is going to be the embedding, the image of phi. The image of phi, look at P. If we have an arbitrary element of lambda 2C4 written in the same basis, we call it P. It will be in the image if P is decomposable as A wedge B. But this is the same as saying that P wedge P is equal to 0. And this immediately means in coordinates that this quadric is equal to 0. This is the Plucker relation. So since phi is injective, the image of phi is isomorphic to G2,4. With this Plucker relation, what do we do? Well, this projective variety, what we have obtained is that is Plucker embedding. To its Plucker embedding, we can associate this coordinate algebra defined by the lambdas ij that correspond to the coordinates in the projective space. Sorry. Modulo the ideal generated by the Plucker relation. This is a presentation of the coordinate algebra of the Grassmannian. But more important than this, or perhaps also very important, is that this coordinate algebra can be retrieved as a subalgebra of the coordinate algebra of SL4. How do we do this? We take here a general element of SL4. We have to take the two first column vectors, and then we compute all the possible minors among them. And then all the relations, according to invariant theory, all the relations that these minors satisfy are exactly the Plucker relation. So we can see the Grassmannian, the coordinate algebra of the Grassmannian, as the algebra generated by Dij inside SL4. And this is what will be useful for the quantization. We are going to mimic this map from one algebra to the other to obtain the quantization. Here we can see from the Plucker relation what are the points at infinity. See that we had that the big cell was, the condition was that y12 was different from 0. Now, if we want to see the points at infinity, we have to consider y12 equals to 0. And then we have two cases. Remember that y34 is accompanying lambda or y12 in the Plucker relation. So we have two possibilities. Y34 is different from 0, in which case we can set, using the freedom of the projective space, we can set y34 equal to 1, and then this equation is just is a cone. Or we can have y34 equal to 0, in which case those coordinates disappear, and this is a quadric in the projective space P3. So let's go now to the quantum picture. Then we make here some connection with the last seminar given by Junaid. We are going to use a quantum group to quantize the conformal group and quantize all the structure of homogeneous space, etc. We are going to translate it to the quantum setting. Well, very briefly, what is the quantum group that we are going to use here? Imagine that we have an algebra of generators that satisfy these commutation relations, where Q is an indeterminate, is a parameter, in fact. And if Q is equal to 1, we recover the standard commutative Rn space. So in this space, that is a non-commutative space, we have the left and right action of, we can wonder what is the left and right action of a matrix of indeterminates Aij, what commutation relations should they satisfy to preserve this form of the commutation relations in that space. So this happened that this problem has a solution. This was done by Manning. And these are the commutation relations, are not very difficult, but it is sometimes it's hard when one makes computations with them. But a matrix that whose entries are elements satisfying these commutation relations, we say that they form a quantum matrix. As I said before, we have, since we are talking about algebras, we have coactions of the matrices on the space, and we have a left coaction and a right coaction. At the same time, we have a coproduct in the algebra whose generators are the entries of the quantum matrix. And this coproduct is what is encoding what is matrix multiplication. So we have, from one part, we have a non-commutative algebra structure, and from other side, we have an also non-commutative coalgebra structure. Then quantum matrices are a bialgebra. It happens that we can put a kind of inverse in this, we can define a kind of inverse that is called the antipode. We can have a unit, and we can have a unit. And if all this happens, then what we have is a quantum group. It's a Hopf algebra that is called also a quantum group. Well, what we do to quantize is something very, very simple in principle. We use the fact that our algebra, commutative algebra, was inside the algebra of SL4, and we imitate this definition. This is now a definition of the quantum Grassmannian as the subalgebra of SLQ4 generated by these determinants. These are quantum determinants. You see that they are deformed by this Q, and Aij are supposed to be entries of a quantum matrix. So we define the quantum Grassmannian like that. Now we have to see if this definition leads us to some place. The first thing that we can prove, and it is a long computation, but we can prove it, that there exists a presentation of this algebra in terms of generators and relations, just like we had for the Plucker relation. We have CQ. This means CQ means the formal power series in Q and Q minus 1. This will be the field that we will use. And we have generators lambda ij, and EQ is the ideal generated by. Now we have to put commutation relations for the lambda ij because they are not the trivial ones. We cannot say it is commutative. So we have to put a commutation relation here, here, and here. And also, as before, we will have a Plucker relation. and the Fluke relation will be modified by some Q's in the appropriate places. Also, for the quantum Minkowski space, we make a definition because we want to imitate what happens in the classical case. So we write a localization of the algebra of the quantum Grassmannian on D12 that would correspond to the determinant D12 in lowercase letters that we had in the non-quantum case. This D12 is a quantum determinant, and for quantum determinants we use the uppercase letter. So we add a generator that will be D12 minus 1, and then we find that this algebra generated by these 4 elements is inside SLQ4 localized at D12. One can prove that there is a corresponding coaction of SLQ4 on the Grassmannian, and a suitably defined Poincare group also has an action on the quantum Minkowski space. I will not write here the formulas because they are not very illuminating, but just for you to know that there exists this correspondence. Let's go now to the super case. I will give some concepts on superlinear algebra just for those of you that do not know, you are not acquainted with what is with the supersymmetry. So a super vector space is nothing but a vector space that has a C2 grading, and here we have expressed the C2 grading in this way. To the elements in V0, we will call them, we will say that they have parity 0 and that they are even. And the elements in V1, we will say that they have parity 1 and they are odd elements. But at this point, we only have a vector space with this C2 grading. We generalize the concept of algebra, although it's not a generalization, but because a superalgebra is also an algebra, but it gives more information to say that it is a superalgebra. It is an algebra that has the same grading as a super vector space. It has the same grading, but the product preserves parities. It means that the product, the parity of the product is the sum of the parities, of course, modulo 2. One can see also, not very difficult to see, that A0 will be a subalgebra of A, while A1 will be an A0 module. This is because of the parities. Even with even will give you even with odd will give you odd. So you will have an A0 module. This is an example, a relevant example of a super commutative algebra in terms of generators and relations. We have even generators that we call x mu equal from 1 to n, for example. And we have odd generators that are sitting in A1 that are the theta alphas, alpha from 1 to m. And for the x's, we have the standard commutation relations. Also, x's with thetas have the standard commutation relation, but the thetas among themselves, they do not commute, they anti-commute. So this is the difference between odd and even generators in this example of superalgebra. Notice in particular that if alpha is equal to beta, we obtain that theta alpha squared is equal to 0. So the elements theta alpha are all nilpotent elements. A supermatrix represents a linear transformation between supervector space. It can be of any kind, but we are going to focus on linear transformations that preserve the grading. If they preserve the grading, this means that the entries of X and the entries of W have to be even elements of, for example, the superalgebra that we described before. And the Y and Z, they must be odd elements of that superalgebra, but in general of any supercommutative algebra. This has a functorial interpretation, but I don't want to enter into that. Just keep in mind that X and W are even, have even entries, and Y and Z have odd entries. If the supermatrix is invertible, it happens that X and W have to be invertible themselves. This is goes in the two directions. It's an if and only if. And for invertible X and W, generalization of the determinant is defined in this way, the way that you see here. Here you see that in order to define these two lines that I write here, they are equivalent descriptions of the Berezinian, and see that for defining the Berezinian, we already need that omega and X are invertible. So this is a difference with the usual determinant, where you can define the determinant of a matrix that is not invertible. It will give you 0, but you can define it. Here you cannot define it, so you are only have to work with invertible matrices all the time. So this is what forms the supergroup GLM, consists on supermatrices GLM/n, supermatrices, and here we represent the dimension of the vector space that supports the defining representation of this supergroup. We represent it as is the dimension of V0 and the dimension of V1 / the dimension of V1. So we have matrices that are M/n times M/n. So they are square matrices in this case, and we take them invertible, then we are in GL M/n. SL, the supergroup that is inside GL, that consists of supermatrices with Berezinian equal to 1, is the supergroup SL/M/n. As for Lie groups, Lie supergroups also have an algebra attached to them. In this case, instead of being a Lie algebra, it is a Lie superalgebra, of course. And the difference between the Lie algebra and the Lie subalgebra is that the bracket is symmetric or antisymmetric depending on the parity of the elements that you are commuting. So we have also a super vector space together with this bracket that has the symmetry properties. This is a Lie superalgebra. What are the superalgebras of GL, or in particular of SL? That is the one that we are going to consider. So this is the example. SL41 is given by this kind of matrices where P is a 4x4 matrix, even. C is just a number, a complex number, a 1x1 matrix. Alpha is a vector in C2, and beta is a one form in C2. In C4, sorry, I said C2 is in C4. We have to satisfy a trace condition that is inherited from the determinant condition for the supergroup, but this is not the trace exactly, it's the super trace, so there is a sign also involved there, and this means that the trace of P has to be equal to the trace of C, that it is C. This set of matrices form a super Lie algebra where the even part, sorry, the even part is formed by the matrices with diagonal blocks, and this is isomorphic to SL4 of course, because we have it here SL4, and here we have a C. For C, the element C, the entry C, we have the field itself as a degree of freedom of the algebra. And this is the off-diagonal blocks form the odd part of the Lie algebra. It has to be a module for the even part. It has to be a module for the even part. So I have put here what is the representation, but it really doesn't matter. So going from Lie algebras to Lie superalgebras is a complicated question, and we can also define semi-simple super Lie algebras. In particular, simple Lie superalgebras are a bit more complicated, a bit more involved than Lie algebras. In particular, they do not have a unique linking diagram. So for SL 4/1, we have 5 different linking diagrams. It means that we have 5 different conjugacy classes of simple systems. And to each of these simple systems is associated a Borel subalgebra and a full flag. Borel subalgebra is a maximal solvable, and they are associated to full flags. So we have 5 different full flags in SL41. I should have written here the different parabolic. Sorry. Sorry about this. I should have written here what are the 5 different parabolics, or at least what are the 5 different full flags that appeared, but I didn't do it. So let's stay with the flag that is useful to us, and that it will give the Poincaré subalgebra, Poincaré superalgebra. We require that this will be a parabolic subalgebra of SL4, just like the Poincaré algebra was for the group SL4. Here is SL41, 4/1. So we require that it is one of the multiple parabolic subalgebras that this group has. And we want that its even part, it contains the Poincaré algebra plus dilations. So as a factor, see that it appears here, this the first diagonal block, we have exactly the Poincaré subalgebra plus dilations. And it appears as a factor. Here we have still some extra element, some extra entry that usually in physics is called the R symmetry, representing the R symmetry, but that doesn't concern us right now. And this is a parabolic subalgebra. It has a two vector and a 2 form as odd part. This is the one that also satisfies a reality condition that is the one that recovers the signature of the Minkowski space. But we don't enter in the reality conditions. We have associated to the parabolic subalgebra, we have associated a super flag. This super flag is what we define as the conformal superspace. And its big cell is what we define as the Minkowski superspace. You'll see why it is like that. See that from the conformal space to the conformal superspace, a lot of things have happened. we have this embedding of this super flag inside these two super Grassmannians. Is the Grassmannian of 2 zero planes in the space, the vector space 4/1, or the Grassmannian of 2 one planes inside the vector space 4/1. Let's start with G20. A 2 zero plane is given by 2 even independent vectors, and this is an even vector. You see that we have even entries here. A1 to A4, B1 to B4 are even, and then in the odd positions of the vector space, we have to put odd elements. So in this way, the vector will call this vector that will say that it is even. Again, reorganizing this with linear combinations, we can make this, we can put this in a standard form. Here we have, you see, this A is a 4x4 matrix, unrestricted, and this will be the Minkowski space. And we have a two vector, actually this alpha here means alpha and beta. So it's a vector in C2. It's a vector in C2 dual, in fact. And this would be the big cell of G24. Unfortunately, we started with that because it looked simpler, but this is called in physics a anti-chiral Minkowski superspace. And it is acted on by the Poincare superspace, the Poincare supergroup that has the Lie superalgebra that we commented before. And it acts, see that it acts the same way on A. The Lorentz group acts in the same way that we had before. We have that there is an odd translation that changes alpha. We have the action of one of the SL2 on this covector. And we see also that this translation it generates also a translation for an even translation for A. Then we have the action of the Lorentz group, Y and X minus 1. And then we have the standard even translations. This is the big cell of the other Grassmannian. See that it has the same dimension. We have a 4x4 matrix here, a 2x2 matrix here, sorry, that is unrestricted and constrained. And here we have a 2 vector. So a vector in C2 that is odd. And this in physics is called the chiral superspace. So to obtain the big cell of the flag, you see how was the flag was inside this, the product of these two Grassmannians, but we now need that the 2 zero plane appearing here has to be inside the 2 1 plane appearing here. So this will give a condition on relating the big cells of the two Grassmannians to get the big cell of the flag manifold. This is what is called the twistor or incidence relations. Well, there is an action of the Poincare group that is given here. Probably is not very illuminating because it is not put in the standard form of the action of the Poincare group. We still have here the translation, the odd translations, we have the even translations, but here we don't have a symmetry between alpha and gamma. So there is still, we need to make a change of variables to connect with the symmetric notation that is used in physics. And this, I will just flash the transparency. This is a change of variables either in the big cells that now become they have this expression. Theta and theta bar are in principle independent because we are in the complexification, so they are in principle independent. And we also have to make some change of variables in the Poincaré group. By doing all this, we recover, this is already the standard transformation of the Poincaré action on the super Minkowski space, on the flag manifold, on the big cell of the flag manifold. We have the action of the Lorentz group, L and L minus 1. We have the even translations. We have the odd translations with the action also of the Lorentz group and dilations. And here we have already in symmetric form the fact that the odd translations generate even translation too. So they generate a translation for C. This is related to the fact that the generators of the uniparametric subgroup of odd transformations do not commute in the superalgebra with each other, but their commutator is proportional to the generator P mu, that is the moment or the generator of the translations. So we have the translation superalgebra was an abelian superalgebra, but now the translation superalgebra concerns the even translations and concerns also the two odd translations, and the commutator of phi with phi bar is different from 0. So translations are not abelian anymore. What is the super Plucker embedding? So we first have to define what is the projective superspace. We take the vector space Cn+1/n, and we make tensor product with an arbitrary superalgebra. As I told you, this has the interpretation, functorial interpretation. So here it doesn't matter what algebra you put here, what superalgebra you put here. And the projective superspace is taken as the finitely generated projective submodules of An+1n. They have to be of rank 1, 0. This is the generalization of the projective space in the even purely even case. So we have submodules of rank 1/0, and contrary to the classical case in which all manifolds that were a semi-simple group modulo or quotient by a parabolic, these were guaranteed to be projective manifolds. This doesn't happen for the super case. We have this, for example, these two super Grassmannians that appear here. We know that they do not admit projective embeddings. Okay, but we are lucky enough, and our Grassmannians do satisfy the conditions to be projective, so they are embedded in a projective space, and we can give a super Plucker embedding for them. First thing that we have to realize is that both Grassmannians are isomorphic, because a 2-0 plane in C4/1 is dual to a 2-1 plane in the dual of that vector space. And using that, we can see that the Grassmannian are indeed isomorphic. So we will have to worry about one of the Grassmannians, the projective embedding of only one of the Grassmannians. Where are we going to embed? Well, we do the same as before. We take the two tensors, the antisymmetric tensors in C41. This will give you as a projective space, the projective space P6/4. And why is this? Because now we will have the 6 even usual antisymmetric tensors, plus now we have phi wedge phi. epsilon phi with epsilon phi. This is an even because of the anti-commutation of epsilon phi with epsilon phi. This is not zero. These are even, so we have 7 even, and then we have 4 odd. So gives a projective space PS/4. As before, demanding that a generic element in lambda 2 C41 be decomposable, we can describe the image of the map, the same map as before, the map that will take our two plane, the two vectors that generate the two planes. There will be 2 even vectors, and then send it to the projective space that we computed here. So with a similar argument, lambda 2 C4 1, a generic element will be in the image of the map if it is decomposable, and then this condition is given by the super-Plucker relations that define an homogeneous ideal in the coordinate superalgebra of lambda 2 C41, that is C7/1. These are the super-Plucker relations. We have the Plucker relations among the even generators. Then we have added these other super-Plucker relations for the odd ones that I denote with a delta. Then we have these 2 other relations between odd and even generators. Now we have also, as in the classical case, a presentation of the Grassmannian coordinate superalgebra together with its embedding in this way. This is a presentation of the Grassmannian G2/0 0 inside 4/1. So we have the DIs, we have the deltas, and we have the D55 modulo the Plucker relation, the ideal generated by the Plucker relations. So we have 2 Grassmannians. So we have P6/4 times P6/4, and this can be further embedded into one single projective space. This is called the Segre embedding for the classical case. Here we have the super Segre embedding, and as you can see, the coordinates in this, the projective coordinates in this bigger projective space are just multiplications of the coordinates in the smaller projective spaces. In our case, for the flag 202141 to be embedded in a projective space, we have the big projective space is P64/56. I don't know if there is a smaller projective space that where you can embed the flag, but this is for sure one projective space. So FL, the flag that we are considering is inside a projective space, so it is projective. Now we have a presentation of the flag as the algebra generated by variables indeterminates that I call D, delta, and D55. I call it for the Grassmannian G20, and D star, delta star, and D star 55 for the Grassmannian that is 2,1. And this modulo some ideal, and this ideal contains the Plucker relations for one Grassmannian, the Plucker relations for the other Grassmannian, plus some incidence relations that relate the coordinates in both Grassmannians. These incidence relations that we saw before for the big cell now can be put for the Grassmannian. Here I have used an homogeneous notation, looked at J goes from 1 to 5, so this includes the deltas and includes also the D55. this is the Plucker relation. Sorry, this is the incidence. These are the incidence relations of the flag. As in the non-super case, these two Grassmannian can be, the algebra, the coordinate algebras of this super Grassmannian can be seen as subalgebras of the coordinate algebra of the supergroup. How do we do this? So if we have an element of the group, a generic element of the group, we take the first two columns. We take all the possible minors in between those two columns. And then we get these elements in SL, these elements in C of SL4/1, and this generate inside that coordinate algebra, generate the algebra, the algebra of one Grassmannian, the Grassmannian to 0. Look what happens when we want to compute the Grassmannian of the Grassmannian to 1. We want to compute the same determinants for the Grassmannian to 1. Since we have to take the transpose -1, then it becomes this horrendous expression. But it's hard to compute, but it is computable still. So in this non-quantum case, you can still compute, and you can have together the di's with the d star i's, etc. Here, these b's are Berezinians, and these deltas are determinants. Okay. All the Berezinians, yes, of course, all the Berezinians appearing here are assumed to be well defined. So in fact, we are considering an open set in SL41. This is how they look, the Plucker relations in if we take supersymmetry equal to 2 instead of equal to 1. They become rapidly, they become growing. The generic case can be obtained for n equal 3, for supersymmetry n equal 3. This can be also computed. It's not a problem. It's only you have to sit and write down the Plucker relations. And we also have here an injection of the coordinate superalgebra of SL4/2. Well, this was about the quantum. Now, what do we do with these things to quantize? We would like to have here super determinants. Okay, and this we will have, and we can quantize this manifold, this Grassmannian. There is no problem. The other Grassmannian, if we have the d stars alone, then we can forget about these expressions and then quantize just in the same way that we did for the first Grassmannian. But if we have to put all of them together, like it happens in the flag, then we would have to quantize all these expressions to find quantum equivalents in the quantum group, inside the quantum group. And this we didn't do, we haven't done it. It is impossible to do. It is impossible to do it. So we quantized the Grassmannians, but for the quantization of the super flag, we didn't compute it explicitly. We had an argument to show that there exists a deformation with the appropriate characteristics, but we don't have the specific explicit superalgebra associated to this super flag. Okay, so this is all I had to say. Thank you very much for your attention.
Thank you very much, Professor Maria. So are there any questions from the audience or comments? So we have Junaid with us too.